Hi guys, today we're going to start A2 physical chemistry. Okay, and we're going to start with thermochemistry. Can you see here? All right, thermochemistry. Well, the first thing we start with, of course, is this thing called lattice energy. Okay, I'm going to show you here. Now you can see here thermochemistry too. The first part is here: interpret and explain qualitatively the trend in thermal stability of nitrates and carbonates of group 2, right? Down group 2, we have already done this, okay? To explain this, we've done this already in your AS, okay? Only this part here we will do, okay, of solubility of hydroxides and sulfates in terms of heat of hydration and lattice energy. So before we do this, we need to do the first part here, which is lattice energy, okay? Okay, now we're going to do this one first. Today I want just to do this one here. Explain in qualitative terms. Okay, qualitative terms. Hopefully we can do this one. Okay, the effect of ionic charge and ionic radius on the numerical magnitude. Okay, the size of this energy. But before this, we need to explain this part here. Okay, this energy, and also this part here, we go to this part here. This part here. Wait, okay, this part here. Okay, part 4 first. So if we can finish this part, then we go into this part here. Okay, explaining this thing here. So the first thing we need to do is define what is lattice energy, and also then use the Born-Haber cycle to calculate, okay, the lattice energy of ionic compounds. Right, now let's go to this thing here. Remember, define. Now, but you must remember, in lattice energy is to do with ionic compounds. Right, now in your, if you want to put it nicely, see in AS, right, we concentrate on covalent compounds. Okay, in A2 you concentrate on ionic compounds. Right? I'm going to give you a comparison on what we want to do here. Okay? On I think I use a black pen. Right? Okay, black pen. All right, now here. You see, for example of a covalent compound is the heat of formation of HCl. So what is the Born-Haber cycle, or we call it the Hess law? Okay, Hess law. So the Born-Haber cycle is not said here, it's not used here, but here they refer to it as a Born-Haber cycle. You can go and find out why, okay? Born-Haber cycle. All right. So in this case here, to draw the whole Hess law out, or the whole conversion or formation of the covalent compounds out, we need to go through all the heat changes. Some are measurable, some are not measurable. Okay, through Hess law we can measure anything. So a great example, of course, the formation of HCl. So heat of formation. Okay, with all standard states. Okay, of HCl, which means 1 mole of HCl, right, formed from its elements, which is H2 gas plus Cl2 gas. That's not okay. Since 1 mole, the heat formation means that 1 mole of the compound formed from its what? Elements there under standard conditions, which means it's gas as well. So it's half here and half here. Now this is what you learned in your AS, isn't it? Right? Here you have the same thing here. I want to form 1 mole of my ionic compounds. You apply the same heat of formation definition. And forming here, well, here's 1 mole of your NaCl. Okay, positive dot Cl negative. Right? So I'm forming from my elements, which is sodium solid plus half Cl2 gas. Yes, not. This is also called the heat of formation, right? So these two terms, heat of formation, is applied for any type of compounds, covalent as well as ionic compounds. It's a formation of 1 mole of the substance of the compound from its elements at standard condition. So it's 1 mole here, so it's 1 mole. That's why, sorry, 1 mole. Okay. That's why we balance off is 1 mole here and half mole here, right? It's half mole here and half mole here, okay? So to fulfill the requirements of definition of heat of formation. Now, how do we go about this? Now, in this case here, they don't form straight away. Hydrogen here must break the bond, isn't it? So from here, it goes to what? H gas, right? Now, this heat change is called the heat of atomization, right? Or is called what? Is equals to half of bond energy, isn't it? Right? Now, bond energy, as you remember, is the energy required to break 1 mole of the covalent bonds. Now, you refer to well, your AS, okay? Now, here's what it says. See? Now, in AS, I give you two definitions here. I'll put them draw first, okay? Draw first. Okay, we go to here, right? So here, this is the part that you require. Bond energy is the heat is a bit bigger. Very good. Thickness. Okay, so it's the bond energy, remember, right? It's the heat required. Required means what? Endothermic. Very important, huh? It's very required to break 1 mole of the covalent bond to form these gaseous atoms. This part here, we don't want anymore because why? Because of the definition. You look at it here in your syllabus, all right? The syllabus on top here. Okay, see bond energy? Where's the bond energy? Okay, see here. Bond energy, you will always say bond energy is positive. Why? Is the bond breaking? Okay, but Less energy is a bit different. Now, I'll let you have a peek first, okay? Right? Is the bond forming? See now, it's negative, see now. It's positive. Okay? Why positive? Because you look at your data booklet, it's all given there. Your bond energy is given, but your less energy is not given. Okay? Well, sorry, I don't know. I was supposed to have it straight away here. Never mind. Okay, here we are. Okay. No. Okay, here. See now. Bond energy is here. So bond energy is here, average value is here. All this is positive. Eh? So the sign here is positive, right? You put the drawing again. Okay, see, it's positive here. Positive here. Because it's referred to what? As the bond what? Thickness. Okay? As the bond breaking. To break one bond. See now. So for bond energy there's a heat required to break a mole or 1 mole. One mole, okay? 1 mole of a covalent bond. Okay? Okay, so in this case, I'm breaking my H and my H here. So this is to break one mole, okay, under standard conditions with gas. To break 1 mole here, I will get 2 moles of gaseous hydrogen atoms there. So this is equals to, if you look at it on top there, all right, hydrogen here is 436. So here is 436. So this, remember, for positive 436. Why positive? You break a bond, isn't it? This is stable, isn't it? To break, you get here is 1 electron. So it's like you break to break the bond. Okay, so this is called the bond energy. It is in lower 6, right? But you can also refer to the same thing as your heat of what? Atomization, right? Okay, it means to form 1 mole. If you form 1 mole, it means to be half of what? 436, which is what? Equals to positive 218. That's that. Okay, so the difference between bond energy and Lattice energy is one is to break bond, one is to form a bond. Okay, now let's go back to the part here. Right, so here I have got, of course, here you can see heat of atomization is equal to half the bond energy, which I showed you just now is equal to how much? I forgot. Let's refer to this again. Right, 218. So this is 218 here. Okay, positive 218. I put here positive 218. Okay, we put nicely here. Erase this part here. Erase too much. Never mind. Do again. Okay, right? From here to here, the arrow. Right? So now this is ready because what? For hydrogen atoms, there's one electron now. Yeah. So it's a free radical. Remember now? Okay. So for chlorine, same thing. So to go to here before it can react, it must break the bond, is it? The chlorine bond to give you 2. Remember, if I want to have 2, right, it's a whole bond energy. If I want to have 1, right, gas. So in this case here, your chlorine dash chlorine here is your gas. So to break this bond here, right, I get chlorine 2, right, which is here to be 7 7 electron, yeah, right. So this is called the bond energy. And given here, if you refer to your data booklet, right, for chlorine here, famous. Now it's 2, 4, 2 here, but sometimes it's given as 2, 4, 4. Okay, so don't worry. Follow the data booklet. Okay, sometimes if they print out, they might give you 2, 4, 4. So half of this is what? Go by 2, 1, 2, 2. Okay, okay, or 1, 2, 1. Don't worry, you follow what they give you in exams. You don't be too smart. Okay. Okay, so let's say this is a 1 to 1. Okay, so the bond energy is 2, 4, 2. Okay, positive. So here's the atomization. It's equals to positive 1 to 1. So from here to here is to form half one mole of Cl, which means here is 1, 2, 3, 4, 5, 6, 7, etc. So this is your well, can see the atomization. Okay, this equals to positive 1 to 1. Yeah. Yes. So now, but when this plus this, give it this one here. What is formed? The HCl is here. Dot cross. What is formed here? It's all gas in it. From here to here, it's a formation of 1 mole, isn't it? Formation of 1 mole of your covalent bonds, isn't it? Yes, which means it's called what? Bond energy. Yes, not? Yes. Of course, in this case, I can find it from here. What is the value? Because it's given in data booklet. HCl here. Yep. Right. Now formation. If you, now this to break the bond, no, it's positive 4, 3, 1. So if you form the bond in this case here, I will have negative negative 4, 3, 1. Yes, not? Yep. Yes. Right. Because one bond is formed. Form means what? This is from 1 and this is 7 here electrons. It's stable here. This 8 is it not? 8 here. So this negative here. So you must know how to use it. Of course, with the Hess law, the heat of formation here. I'm going to use blue. Okay, here, right? If I put down here, okay, heat of formation, all right, of HCl is equals to the summation. Remember, this is the initial, the heat change, right? And this is the final. Okay, so it's equals to the summation of all these heat energies in. So heat of formation equals to plus, always put the sign here, plus 218. Okay, plus, okay, bracket here, plus 242. Okay, okay, plus, of course, now heat, this is from here to here, is minus 431. It's not. So in this case here, this is a root 1, right? It's a root 1. This holding here is a root 2. So you can find out, yeah, heat of formation. Okay, now this is covalent bond. Now I want you to see the difference between a covalent substance and an ionic substance. Okay, now the root is about the same one. Of course, they go to different sort of kill the mosquito. Lots of blood. Okay, now here what happens? How is 1 mole of a ionic substance formed? Very simple. Okay, now from sodium, which is the metal, course, sodium will go to first. All right, sodium gas. Right, from solid to gas is heat of sublimation. Or 1 mole to 1 mole here, you can also say the heat of what? Atomization. That's not. Okay, when 1 mole of a substance, 1 mole of a gaseous atom is found from its element at certain conditions. Okay, it's called. There are 2 terms for it. Okay, right. Now I'm going to show you here what the value is. I didn't mean to use one, but then I use it already. Never mind. Okay, here. Okay, right now this is called the Born-Haber cycle. This is the actual one, but I'm going to draw the Born-Haber cycle in the Hess law or in the AS manner. You can use either one, but this one here with all these different things. This is the Born-Haber cycle. Sorry, with this one here. But this is actually the Born-Haber cycle. Okay, I'm going to show you this up to scale. Okay, right now here, of course, now I use here easier. Okay, so now the first, of course, is here heat of atomization. Yep, positive. Why positive? Because I'm breaking the bonds here from here to here. Okay, what bonds are broken? What bonds are broken? Huh? This metal, isn't it? Right? This is the well arrangement of particles in a lattice. Okay, so they are all bond, and remember this is all your electrons and blah blah blah. Okay, this is your lattice energy. Yeah. So like this is your metallic bonds. So to break this one here, it means this is individual, right now. It means no more here light only. Okay, so here to here is called here atomization. Same. The way atomization is the same as in your HCl here. See, this part here. Okay, of course this is your gas. This is your solid, right? So like here. So the first part here. All right. So now your Cl also, now you can go on one shot here, right? Or you can start with Cl first. Doesn't matter, man. Okay. In the reaction, both are started in a way, in the same way. Now from here to here, same. I want to form 1 mole. 1 mole. Of course, I need only half of Cl2, isn't it? So from some here, same thing. It's 1, 2, 2, or 1, 2, 1, 2, 2, or 1, 2, 1. It depends on the same. Okay. That's given. So the gas is swapped. Now this and this cannot react. No, why? Because sodium won't form a covalent bond with it. Okay? Cannot say that. Right? Cannot, because 2, 8, 1. This one 2, 8, 7. Why can? Okay, right? Right? Cannot. So what happens is that this fellow here, right? This fellow here loves to give away the electrons. Okay, to this fellow here. So what is this? From here to here is your first energy, which is found in your data booklet. Remember, AS here. See, sodium. Okay, see, okay. Yes. Okay. So this is the one here. 494. Where is it? Okay. So 494. So it's here. Now sometimes you can give 500. Doesn't matter. Okay, 494. Sometimes this is from another book. Okay. So this is the first IE. So from here to here it has lost 1 electron. So I can put the electron come out here. Now this further here is 287. What it does is it will accept electron. Okay, now this from here to here is called the electron affinity. They will ask you in your A2 the definition for electron affinity. Now here it is. All right. It's a heat change when 1 mole of the substance of atom or ion. Remember, of the substance here is general term. You can refer to an atom or an ion. Why? Later, except 1 mole. It's always 1 mole and 1 mole. Okay, now for oxygen, right? Now 1 mole of the substance atom. In this case here, now this is called the first. This is called the first electron affinity, AEA, of oxygen. Okay, O. So 1 O is 2, 6. Okay, the electron configuration. Plus 1 electron, it go to 2, 7. It's not. Now it's negative, which means 6, 7, 2, 7 is more stable than 2, 6, 9. So it gives out heat. Yeah? Okay. That's what it means. That's why it's negative. Give up 1 for 1. But the second, they call it second electron affinity, is equals to positive. No. That means it's 2, 8 here, 2, 7 here. Talking too fast. Okay. 2,7 here goes to 2,8. You might say, oh, sir, 2,8 is more stable than 2,7. Yes, true. But then to get the electron inside here, right, you have to put in energy. That means you give the electron energy to push himself inside here. Why? Why you need energy? Because this is negative, and electron is negative, isn't it? So there's here repulsion. Okay. So to overcome the repulsion, you must provide energy. That's why it is positive 790. Right? So that the two things you add up here will give you the total here required for oxygen. So if it's for chlorine here, it's very simple. Chlorine here is negative because you're going to 2,7 here to 2,8. 8 is not okay. Now this is of course 2,8 right now. So it accepts this electron here. Electron goes to here. Okay. So it's minus 39669. Now don't worry about this further. This one I got from another book, so it depends on what they give in exams. Okay. So now these two fellas are ready to attract each other. Talk about bonds. Earlier for HCl, the attraction to form is covalent bonds. Here the attraction is what? It's within ions. From here to here, this is called the lattice energy. Okay. Now let's look at the definition for lattice energy. Okay. All right. Okay. Right. Lattice energy is of an ionic compound. Remember, lattice energy is always for ionic compounds. Whereas Born energy is always for what? It's always for covalent compounds. Okay? It's 1 mole. 1 mole, right? Of a covalent of 1 mole of the covalent bond, which is broken to form is gaseous. Gaseous what? Atoms. That's why it's always positive. Here's the form. It's a hit of formation of 1 mole. The key is 1 mole here of the ionic compound from what? Gaseous ions. Right? Under certain conditions. So remember here, so the lattice energy of sodium is, the answer to write the equation up. So you start with this one here, 1 mole. Now you don't have to put the positive negative sign here. All you do is I put NaCl solid. Okay, you can put the positive negative if you want to. I mean, this is just to show you you're very smart as well. Okay, now from the elements. The elements, sorry, not elements. If it's elements, now if it's this one here, if it's Na solid plus half Cl2 gas here. What is this? This equation called? Is a what? Formation. Did I ask for here formation? No. Lattice energy here, which means I want to form this one here. Same. This is same. From what? What they start from is very important. From is gaseous ions. Okay? So it's Na plus ion. Yes. Plus gaseous Cl minus gas. See, since it's 1 mole here, it'll be 1 mole here. So this heat is called heat lattice energy, Le. Or sometimes the delta H, they put here LATT. See? So if you want to find the heat, you want to give me the lattice energy of magnesium chloride. That means the thing here, the product here must be an ionic substance, magnesium chloride. Okay? So this is a solid. Why? Group 2 is in. Group 7 is in. From what? Metal, non-metal give you what? Ionic compound. So 2 plus here and the same here. So if you want to write your lattice energy, it must be, now here's 1 mole. So what are the ions? Must be gaseous ions. So Mg cannot put metal here. It must put 2 plus here, gas, right? Okay, and 2 Cl minus gas. So this is called your lattice energy. Okay, standard. If I want to write from here to here is a heat of formation, I must start with Mg. Solid now. Okay, from its elements as elements, this is gaseous ions, this is elements, plus Cl2 gas. So this is a heat of formation. You see the difference? But you always use these two things here. Okay, like you see here. So now let's go to give an example, a question. Okay, of lattice energy. Oh, sorry here. I forgot to write here. Now page 23. I got it here. Body control 23. Okay, I'll give you the past questions. Okay. 23. See, yeah? One of the reasons for the melting point of magnesium chloride is very high because it is a fairly high Lattice energy. Why? Because magnesium chloride is what? It's an ionic compound. Explain the term Lattice energy. Write a balance equation including state symbols, okay, to represent the Lattice energy of magnesium chloride. 4 marks means 2 marks and 2 marks. Okay, 4 marks here. Right, and let's look at the answer script. Okay, here we are. All right. Am I correct? No, this one. Sorry. Okay. Remember, what is the definition for Lattice energy? The heat energy change. Okay, let's highlight here. Okay, let's put red color. Okay, remember, energy change or heat change when 1 mole of the solid compound or solid, why solid compound? Because ionic substance are high melting point, so it's always solid compounds. Okay, so of an ionic compound, it's too fat on a big dinner. Okay, of an ionic compound. 1 mark is formed from its gaseous ions. You know, they put it black, which means that you must put it. You must include this one. Okay, you must say add what? Add RTP. You want to put even on the perfect. So 2 marks here. You know. Okay, right now they ask you for what is the equation for this Lattice energy for magnesium chloride. So here's, remember, it's 1 mole. You know? So it's 1 mole. Say 1 mole of the compound formed from its gaseous ions. Ions, Mg2 plus, not Mg. If it's Mg solid, it means it must be heat of formation. So it's 2 Cl minus, okay, gas. So charges and balancing. Charges here, 2 correct, and balancing. State symbols. The symbols are important. Gas, sorry, 1 mark each. Okay, right? So I've given you this example already. You can do the rest yourself. I don't want to waste too much time on it. Okay. Now here, let's go down to now actually how do we actually calculate for the lattice energy. Okay. I'm going to give you examples after examples because this is what it comes up normally. Okay. Now let's go to here. Okay, the first one here, let's go back to sodium chloride. Okay, now here. Okay, so we'll put this smaller. Okay, so remember here, they would, to find this further here, to find your less energy, right? So this is very badly done now. Okay, you know, sometimes I'm going to do that. Less energy should be of sodium chloride. Okay, now it has like gone up, you know, out of sync. You know? Okay, now I think you're smiling at me to look at, know that. Okay. So now to find question mark here, you must be given all the other heat change. So heat of formation is given is minus 411. Okay. So because of the bond, because of Hess law, I can say that now this is root 1. Right? Root 2 is from here to here. That's not okay. Root 1, root 2. So very simply, you can just add up the whole thing here. All right. You put out here. Put this smaller again so it can have more space to write. So I can say that now to find some here, to find this here, of course, I put the formula first. Delta H of formation. Okay, is equals to, well, that's right. Now put all the signs here, and you add up. Put the signs here. Can put a bracket first. Positive 108. Okay now. Okay, plus. Then put here positive 500 here. Whatever. Positive plus positive 121 or 122 lah. Positive electron affinity, which is minus 369, plus here you put lattice energy. You don't care, the sign will come by itself. So now this is equals to what? It's equals to minus, okay, minus 411. Okay, so you add all this further up, right? And you bring this thing over here, and you find here the answer will give you the heat of the lattice energy. Okay, understand? Okay. Now this is using the cycle method. You can do cycle method, or sometimes they will actually give you, right, in terms of this. Now this is called, this method is called the Born-Haber cycle. I just want to tell you a big thing here first, okay? Because as I said, this is normally given, and they will ask you to account for the name of all these things here. Can you see now? Okay, I'll just go to the whole thing first, okay? So where do you start when you want to write, when you want to draw this Born-Haber cycle? You always start with the heat of formation. Okay? Now remember, heat of formation is what? Sodium solid plus half Cl2 gas goes to Na positive dash Cl minus. Yeah, sorry. Okay. So where shall I start with? From here. Okay, right? Now heat of formation is all, in this case here, the ionic substance always exothermic. They'll give you, okay, first give it as -4. That means it must go down here. So this point here, if you put this, if this axis here, it will be 0 here. Why 0? Remember in your AS, let's go back to AS first. Oh, forgotten. Okay, AS, remember not? It says here. Right, this part here. All elements, sodium, solid, and chlorine, whether it's half or 1 or whatever, as the conditions are taken to have what? 0 enthalpy change. Okay? We're talking about enthalpy, not entropy. Entropy is different. Okay? So taken as 0. So here I can say, oh, okay, since sodium here is an element, chlorine here is an element, and of course it's RTP. How do you know it's RTP? Because of the states. Solid here and gas. So this is 0 kilojoules per mole. Okay? So the form here, let's go down here. So if you want to put the value, right, from here to here, so if you want to put a value on the axis here, is -411. See now, sometimes they actually give you the value here, so you have to calculate out. See now. So now here is where you go step by step. All right? Okay? Now, so I want to start. I can start from sodium first or chlorine first. Up to me. I start sodium first. So from here to here is the heat of atomization. Do you see it? Okay, I'm going to make it bigger so that you can see. All right? Okay. Yeah. So from here to here, I put up here. Go up here is my plus 108. That means that you want to put the value here is positive 108. Okay. Now this is the axis. This is the value here. From here to here is 108. Right. So now half Cl2 is I can put on the same level. Why? Because it's equal to 0, isn't it? Yeah, why 0? Element as standard conditions. So 0 plus 108 is still 108, isn't it? Yeah. Yeah. So now again, here from here is first IE plus 500. So here to here is 500. Now from this level to here, this is 500. So now this value is what? It will be 108 plus what? 108 plus 500. It's be 608. So this value here, if axis here, the graph is positive 608. You see now? Okay? So this is a summation of all the energies up here. So I can still put the half Cl2 on the same level here because what? Is equal to 0, right? Element cell condition is equal to 0 then. All right, next one here. I want to continue with sodium. I finish with sodium first. From here to finish already. Sorry. Now, so now I deal with chlorine because this is ready to form the ionic bond ring. Because it's 2,8. Yeah, it's 1 mole of your gaseous sodium ions. So now Cl2, the first step of course is to atomize it. Right? Here to here, of course, is half bond energy or positive 1 to 1 or 1 to 2 up here. So here to here is not here. So of course, from here to here, I can put what? Is what? Is 608 plus what? I put here is 1 to 1, so it's 1 to 1. So it's what? 7 to 9. So this value here is positive 7 to 9. See now? Okay? So now I got this one here. Now this value here is counted for from all this thing now. Yeah. Right? So I can put here. Plus this 1 electron here. From where? From my Na. Actually, should be 1 electron here when I put out, okay? Right? Plus a Cl gas. It's not from here. So now from Cl gas must turn to Cl minus now, okay? Here. So this electron affinity is -3,6. So minus means going down, okay? So it's 729. 729 minus this positive minus here is 369. So 0 here is 6 here, carry 1 here, 6,3. So it's positive. Okay? So here finally you reach down to this part here. Okay? This is positive what? 360. Okay? Or here you give up. Here is the change from here to here. Yeah? Of course, now this is not in correct spacing. Never mind. So now I've got this part here. See, I'm ready to write my lattice energy because it's 1 mole of my gaseous, 1 mole what happened. Okay. Right, this is 1 mole of my gaseous. What happened? Okay, never mind. Okay, right. 1 mole of my gaseous ions. 1 mole of my gaseous ions to form here what? This name, right? This is actually 1 mole of my ionic compound. Right now. So from here to here is called the what? Lattice energy. Formation of the bond, what bond? Ionic bonds. So this is given here. Now there are a couple of ways to solve. There are 2 ways actually to solve this thing here. You can say follow the arrow. Say follow the arrow. Follow the arrow. So now I'll start with this one here. Okay. So I'm going to use green color. Okay. So I like the different colors here. Use full advantage of this Huyon stuff here. Okay. Right now, this is the first step. Okay. The second step is, okay, going up. See? All right. I'm going to put like that here. So it's going up here. All right. Remember from this step, up, and then follow the arrow, going down to here. The 2 arrows, the energy must be equal. Okay. So the first arrow from here to here downwards is what? Is 4. So here's now. Okay, equals to the other arrow. Okay, here, remember, now here's 1, it's not here. You to do the arrow method, you have to be careful of the signs. Okay, here to here is positive 108. You go up here is positive 500. See, positive 500. You go up here is positive 121. Right? Then the arrow goes down here. It's negative, negative 369. See now? Negative 369. And of course, plus the LA. Now here you don't put any sign. You don't get, you will come up 1. Okay? You can go back and do the whole thing, add up everything according to arithmetic. This one is plus and minus, the whole thing is what? 3. Okay? You do this whole thing, bring over here, you get this answer. Okay? Now this is what they call, this method is called the Born-Haber cycle. Okay? So if they refer to Born-Haber cycle is for ionic compounds and is like doing the whole stuff here, the graphical method. Okay? Right? Now, of course, you can do it in the hash law method like here. Sometimes the space provided you can't do something. But either way, you get the mark. Okay? Right? Now, let me show you for sodium oxide a question here. I think it's page 20, 26, 25, 26. Okay, 26. All right, here. See now here they give you in terms of the Born-Haber cycle. See, okay. Write an equation to represent the Lattice energy of sodium oxide. So of course it's what? All right. Remember 1 mole of the substance form. 1 mole is one here. O solid not. All right, because Na2 is positive. Dot what? O2 minus not. Yes not. Yes not. Okay. From is what? Gaseous ions, which is Na. 2 of them positive gas, plus 1 of them O2 minus gas. Yes, this is your equation for the formation. Okay, now, okay. Yeah, for formation of the ionic bond, or is for Lattice energy. I repeat again. If you want to do, if they ask you for the heat of formation, just the heat of formation, right, of sodium oxide. What is it? So you put 1 mole of your sodium oxide here, same as this one here, solid. From is what? Elements here, which is sodium. 2, solid state or your metal plus what? Half of O2 gas. Now this is your heat of what? Heat of formation. This is what? Lattice energy. Do you see that? I want to repeat again so your big lumpy head will remember. This they are both formation. They are both formation. You form something. This form from its elements, this form from its gaseous ions. Is that clear? So now they give you the whole thing. Okay, the Born-Haber cycle shown may be used to calculate Lattice energy. Okay, and blah blah blah. So they're very kind. They draw the whole thing here. Of course, they will ask you what does it mean. So where do we start first? Remember, start from the elements because these are elements here. Okay, right? sodium solid plus O2 gas. This is of course your elements at standard condition. Now going down, of course, is the formation or not. Okay. So this will be the heat of what? Formation or not? Yes, because they will ask you one. What is the, see, in the space below, identify the space A and B, so including the appropriate state. Identify the enthalpy changes, label 1 to 4. Okay, so 4 is what? 4 is your heat of, and any change is of heat of what? Formation. Okay, or you can say Na to O. All right, now step by step. From the first step, they tell you is for atomization, not for your oxygen. So fine enough, that is it, right? Now here they give the name. They will expect you to later calculate the value here given here. Okay, see, enthalpy change of atomization is plus 107. Okay, right? So here is atomization is equals to plus 107. Okay, right? So remember, that means what is A here? It should be what? 2Na gas, isn't it? You would ask for A, isn't it? So A is here. Here is what species Na gas. Okay. Now from here to here, Na gas go to Na plus gas. So what is this? What is this? It's a heat of ionization. 2 doesn't change anything. It's called enthalpy change. It's called the first ionization energy. Yep. From here to here. So O half O2 is the same, right? True. So I finished. I've got ready my sodium thing to react already because it's 2, 8. Actually, by right, you should put plus 2 electrons here. You want to put lah. Okay, there's nothing wrong. Okay. Now from here to here, of course, now this remains the same, right? So yeah, you're going to change oxygen here. Of course, oxygen, the gas here will have to break to form this molecule to gaseous state O, right? So half of O2 is 1 over here. One. Yes, not because you need only 1 oxygen. So here is the heat of atomization. I'll give it to you. So I put down here plus 248 given down there. Yes, no? It's not right here. Now here is a bit. Here they put it up here, but now from here to here is not. Okay, this is the first electron affinity and second, both combined. Yeah, because it's 2 minus. This is 0 here. Yeah. Okay, it will accept the 2 electrons here. From where? From your sodium. Yes, not. Now you see given down here. They say 2 here, 2 here, 2 here. So I got here first and second. First and second electron. What? Affinity. Right? It's 2 here. Okay? Now it's all ready. Now the value here, of course, you can see from down here. They give it to you. Okay. First electron affinity for sodium is this one here. Yes, second one is this one here. See, it's positive. Why? Because electron is negative, O negative, there's repulsion. So the together here is 798, which is positive, and this minus 141. Okay, so it's 7, 5, 6. It's still positive, isn't it? Right? That's why they're going up. You know? They don't do it separately. You can do it separately, right? Too. But this is the one here, 6, 7, 5. So here is going up here. It's positive 6, 7, 5. Yes. Now I've got my individual species of ions to form my 1 mole of my here. You know, so of course from the top there to form 1 mole of my ionic compound from its gaseous atoms. It's called what? Lattice energy. You know, going down, is it? Going down, of course, is negative, like exothermic. But don't care. Now, as I show you, one way is to follow the arrow. The other way is to just add up this whole thing equals to this one. See, lattice energy is equals to lattice energy. You can say mathematically, lattice energy is equals to right? This one here, heat of formation plus this atomization plus this. What is this? This is the IE plus this one here plus this one here. Okay, it's good. This one, yeah, right. But now, see when you add this part here and this one here, you don't care about the sign. You just add up. You don't care about the positive, negative. Why? Because when you're going down here, it's always what? Negative, isn't it? Yeah. Okay, now try that and see. Okay, now I'm going to do it up this way here. Okay, number 3, of course, what's 3 here? 3 is called the lattice energy. Okay, lattice energy. Okay, so of course in this case here you can see it's given out here. So if you want to put the whole thing here, okay, now let's do it properly here. Okay, all right, let's follow the arrow, right? Because starting I want to go it slowly for you. Okay, the arrow, the first arrow from here to here 4 downwards. There's only one arrow here. Here's the formation. Now how much is equals to is given here. See? Right, enthalpy change of formation minus 414. In this case, you must put the value here. Okay, where to put it easier for me to write? Okay, put it here. Minus 414 equals to. Okay, now this is the downward arrow. Yeah, for the arrow downwards, now upward. Positive. Bracket positive 107. Is it 107? Times 2, isn't it? Let me see. Here to here, atomization. I will check again. Okay, 107 times 2, isn't it? Because there are 2 moles. So 2 times. So I put down here. I'll rub it off first. It's a bit messy, maybe. Okay. I see. Here. Put red. Okay. 2 times positive 107. Must write slowly because I want to get the space. Plus, always plus first the bracket. Okay. From here to here is, remember, 494. So it's 2 times again. 2 times positive 494. From here to here is what? Okay, the whole thing here, the atomization, right? Now here they give you atomization. Okay, atomization here, see, but they didn't give it to you actually. Enthalpy change of atomization is half of one energy. Okay, let's refer to half of one energy over here. O2. Okay, no worries. You can use the data bullet. Okay, O2. Now here's O2. 1 mole is what? Is this one here? So to form 1 mole of your O gas, 96 divided by 2. So it's 2 what? 29 carry is 8. 2 is what? Is positive 298. Okay, positive 298. This is okay, positive 298. Right, because 1 more here. So here going up plus positive 298. Okay. Now then go up here, isn't it? Right? Here is it, right? Then here again. Okay, here of course is your what? Is your electron affinity is here. So it's plus, okay, positive 2. What am I doing? Here's 291 energy. Sorry. Here's 2. Wait, I thought I saw it. Okay, now here, right now, 298 is in. Let's do it again. 298. Okay, now then of course your affinity, right? Is this one here. 657. Sorry, 657. Okay, correct here. This is for here. I was an idiot. Okay. Okay. This is from here. Okay. So plus, right? It's 298 here. From here to here is 298. Right. From here to here is 6. Hurry! All the mistakes, and it's on tape some more. Never mind. This slide is not that smart. Okay. Just very clever. Okay. Positive 675. Okay. Now follow the arrow going up there and then going down there. So I put positive lattice energy, LE as you can. Okay? So of course I add all this up, bring over the lattice energy is equals to minus 414 and bring the whole thing up minus the whole thing here. Yes? Okay? Right? Now you can see the marking scheme, okay? This whole thing here. Now this is under what year? Let's check this out. Okay, I've got it here. 02, 02. Okay, here we are. Okay, so now, right now remember this is your what? What is this? Huh? What is this? This will be your equation for your lattice energy, isn't it? No. One more of this form from is too fat. One more of this form from is what? From is gaseous ions. Okay? No. One mark. All must have all three state symbols. Normally they get 2 marks, but here balancing and symbols and charges all 1 mark. Is okay. The 2 is up to you, but the species is important because this one, okay, 2 must be okay. B must be O gas, not O minus. B. What is B? Okay. What is B? What is B? Okay. Now this is B. Right now, okay. Must be the atom, isn't it? Okay. You put minus here wrong. Right? Okay. First bracket here means that is optional. Or you can use IE, optional. First ionization. So here for oxygen is first and second electron affinity. See now, okay? Right? You can put first electron affinity or second electron affinity. Okay. Or you can use this symbol. EA is understood electron affinity. Okay now. Right? Right? Lattice energy. See, you can use the whole term. You can use LE or this one here. So all these are acceptable. All these are acceptable. So you can see the marking saying what the examiner wants, what the Cambridge wants doesn't matter. I mean, matters in the sense that if they don't bother, as long as you know your substance here. Okay? So 4 is called the heat of formation now. Okay? You put HF as you can. Okay? Right? This is not very good. C something combustion, no. But these are better heat entropy change of formation. Okay? This C is combustion actually. So formation better. Okay? Right? Because combustion here can, because right, you're burning and sodium now. Okay? Now see here. Right? Now see here, this whole thing. 3 marks no. So the first mark, of course, is to show the whole thing here. That means if this whole thing here is correct. Right? And of course, after that, they see your substitution of this value is correct. See now, okay? Then of course, it's this one here. Right? The sign and the vat. Now this bracket here, that means up to you. But normally better put. The sign is very important. Its energy is always negative, isn't it? What's one more of the bond form? Any bonds are formed more stable, isn't it? So it's exothermic, including the sign. Correct answer and correct sign. This is normally 1 mark. Okay? Right? So the answer and the sign. Sometimes if the answer is right, the sign is wrong, well, they will give you, I don't know. Okay? See the correct answer. If that is right, 3 marks straight away. Okay? You can see here, blah, blah, blah. We don't care, okay? Right? We are aiming for perfect answers in. Okay? Can, huh? So I've given you 2 ways of doing it. One, of course, is the energy cycle. Right? One is the Born-Haber cycle. Okay? Now, I want to quickly now do two well, difficult ones. Not say difficult, they are, different. Okay? One, of course, is your barium sulfide, page 30. Okay, let's go to page 30. Yeah? Okay, we need to have time management. Okay, wait, where is it? Sorry, oh, 36. Blind cow, you know. Okay, see, use the following data and the data from data bullet, okay, to construct Born-Haber cycle, okay, calculate the lattice energy, okay. Now here, the Born-Haber cycle is basically refers to a ionic compound. Okay, now you can do the energy level one or the cycle one. Cycle one is easier. So how do we start? We always start with the heat of formation, right? So that's why it's always given heat of formation. So how do we start? Remember here, heat of formation is what is 1 mole of your compound barium sulfide. Okay, solid. Now you should know in your IGCSE barium is group 2, is Ba2 plus here dot sulfide. Yeah, you better know. Tell you don't know. Kick your head. Yeah, okay. So here's barium, right? Solid plus. Now here they don't bother here, but now they may ask you now because sulfur is actually S8. So to be correct, it should be barium solid plus sulfur S8, Hb18 over here. To be perfect lah, this solid, to give you your barium sulfide solid. See now, okay? So here, of course, sulfur is in this form, it's like a crown, okay? This again, of course, is in your AS, sulfur here, 2, 3, 4, 5, 6, 7, 8. So now this is a sulfur bond. You know, so there's 1, 2, 3, 4, 5, 6, 7, 8 on. Okay. So here to break this bond here. So if you look at your data booklet, all right, it's a bit different from here. Sulfur bond. If you want to know, okay, sulfur is it given here? I thought I saw it here just now. Never mind, can see it again. Okay, here. See, I'm a blind cow. See now, it's 265. Okay, but here it means this is the 1/8 of your the whole thing lah. Okay, now. So sometimes they give you S8. No, they are quite tricky nowadays. Okay, so now here is very simple. Just okay, right? And temperature of atomization for sulfur, it means that 1 mole of your gaseous sulfur from its elements in, right? Which is this one now. Which is 1/8 of S8 solid. S8, sorry, go to gas. Okay, yes, 1 mole from this one. Okay, now this is given as what? What is the thing? This is okay. Positive 79. 279. You compare that 279 with here. 279, like 279, it's about the same, okay? Okay, so it can be different. So normally, if they don't give you, use one here. Okay, if they give it here, use one here. Okay, so it will depend on the conditions. So never mind. Now you always start with this one first. Okay, for the Born-Haber cycle. Okay, Born-Haber cycle is for calculation for what? Ionic compounds. Okay, I'm looking at my time much today. This as okay, we put a solid here. All right. Okay, so here to here. Okay, right. So this is your heat of what? Formation. Why? 1 mole of your ionic compound from its what? From its elements in, right? Not gaseous yet. So how does now this one is given as what? It's given to be. I put later I put the thing more time already. So here I go down to, of course, to change to the barium what? Barium gas. Okay. So this is atomization is it here. Okay. Okay, which is positive 180. Okay. Now let's work on barium first. Of course, it undergoes two what? 2 ionization is it. So now this is atomization. So is it given here? Don't have. So you have to look out here from here. I can put one by one, but I put 2 together. Ba2 plus gas. Come out here, 2 electrons. Okay, so I go to my data booklet. All right, I look down as my barium. Sorry, on top here. All right, barium. Okay, now here. It's a second part. Okay, now to the first part. They say, oh, don't have. Mr. Lam, laugh me, oh, you idiot. Barium. Okay, first and second. So it's 966 plus 5502 is 8614. 1468. All right. So this is 1468. So here to this right. To remove it, it's positive 1468. To remove electrons, you need energy, isn't it? Yeah. So electron given up. Okay. Now this I'm ready. I'm ready, man. Ready. Okay. Right, now remember this is the formation. If let's energy, if you got Ba, put blue color lah. Okay, should be Ba. Okay, Ba2 plus gas plus S2 minus gas to give me 1 mole of your barium sulfide. Yeah. So here I got ready here. Now to convert this to your sulfide ion. So from here to gas. Sulfur gas is a heat of what? Atomization is what? Positive. How much? Positive 279. Yes, not here. Okay. Now this sulfur, of course, take in electrons in. Now, so they give you electron affinity for sulfur atom. The first one. Second one. So you can put 2 together. You put one by one up here. Okay, let's say 1 by 1 if you're a bit fussy. S minus here gas. So first one here is how much? Is minus 2, 0, 0. But it's more stable then. Now the minus 2, 0 go to one more to S 2 minus here gas. How much is it? Second one, positive. Why negative charge? They repel each other 6, 4, 0. Okay, so this 2 here is equal to how much? Positive 640 minus 200 overall is still positive. Positive 440. So it's positive 440. Okay, so now this plus this, you're ready, baby. Now this plus electron here, plus electron here. These two electrons come from where? From here, yeah. So from here to here, what's it called? Lattice energy, or delta H what? LATT. You can put the thing here. Right? So here the formation, is it given or not? Yes, it's given as minus 460. So baby, here we have now the by Hess law, you know. You can put by Hess law here. By Hess law. Okay, so root 1 minus 460 equals to root 2. All this thing from here to here. Okay, let's look at the first one first. Okay, barium. If it is, put a bracket better, plus 180, right? Plus 1468. Finish, huh? Okay, let's do the sulfur. Plus 279. Okay, plus this whole thing not. Yep. Bracket plus 440 plus lattice energy. Okay, can solve or not? Let's look at the marking scheme. I don't want to spend. I've got 5 more minutes to go. 09, I got it here. See, I plan my work, man. See it. Okay, see it. Okay. Now 460. 460. Yeah. Next one here. 1468, 180. 1468, 180. Yeah. Look. Okay. Then here is positive 279 and minus 200. Now this whole thing we add together. Okay. This whole thing we add together, which will give you, of course, yeah. Want to hurry also cannot. Okay. This whole thing we add together. We did it. Okay. As positive. What is this? Positive 440. Okay. Okay. So 279 and positive 40. See, okay. See, 79. Yes, not plus LE. Plus LE. See, okay. See. So you work the whole thing out. Make 3 marks, huh? This 1 mark here. Normally 1 mark here. This answer is 1 mark. Each error is minus 1. Okay. And see, plus the minus here. Can do? Okay, now I got just one more to show you because this is what I planned for, okay? Planning. Fail to plan is planning to fail. Now the second one, of course, these are all tricky ones. I want to spend more time for it, okay? Which is page 39. 39, just down here. Just down the word here. Okay. Here. See now. Right? Despite the apparent lack of reactivity of N2, nitrogen atoms have been found to form bonds with almost all the elements from the one nitride, remember? N-3. Okay? Lithium metal reacts with nitrogen, okay? Gas and so okay, to form lithium nitride. Okay, nitride now. Okay? We done before, isn't it? Magnesium produces magnesium nitride, okay? As well as oxide and so forth. Now here, calculate the lattice energy for magnesium nitride using the following data in addition to relevant data booklet. Yeah, very simple. So here, how do you start? Again, you start with heat of formation on, okay? Magnesium nitride and 2 solid. Of course, it's your M2 plus, this is Mg2 plus dot with 3 of them, and your nitrogen is minus 3, okay? 2 solid. So here, of course, you have your Mg3 here. Now, remember, I started with heat of what? Heat of formation. Plus, of course, N2. Gas, this will be your solid. Balance it. 2N on. Yep, this whole thing. This is heat of formation, which is this fellow here. Minus 461. So now go step by step. So the first, of course, is to what heat of atomization. Yep. Okay. go to 3 mg gas, which is 3 times what? Positive 148. Here, of course, then you go to, of course, your heat of atomization, which is your mg, 2 plus gas. Again, it's 3 here. So 3 times your first and second, which is here. You look carefully here. I'm going to go a bit fast here. You have to rewind to look again, okay? I'm sure you can do by yourself. Okay, down here. Okay, magnesium, right? Mg, first and second, which means 1450 plus how much? 736, which is equal to 6821. 2168. Do it by yourself again. Yes, 3 times plus, what's it? 2168. 3 times, no. That's a 3, huh? Right, ready. So here to here, of course, you form your N. 2N gas. Okay, this to break the bond knot. Okay, now see it's very big here. So nitrogen, bond energy for nitrogen. Here we are. Okay, N is triple bond, triple bond. Yeah. Okay, very big. Positive 994. Now sometimes it's given as 996. No. Okay, don't care. I put 994 following here 994. So here to here is positive 994. Okay, to form 2 moles now. Because you break here. Yeah, 2 moles. Okay, break 1 mole and 2 is it. So now from here to here, of course, from here to here, it accepts 2 here, accept 3 electrons. Okay, see? So total electron affinity is the give basically 1 to 3. Okay, it's written here. So I got 2 of them. So it's 2 times what? Positive 2148. That's not okay. So now this passes, of course, from here to here is what? Your lattice energy, is it? Yes. Can do not. So for this one here is equals to, so the answer would be, all right, something is wrong with the dot. Okay, never mind. Okay, let's put here. So the Born-Haber cycle should be minus, see, it's the blue color cannot use, I don't know why. Okay, remember, minus, again, trying to hurry, man, baby. Okay, again. Minus 461 equals to 3 times positive 148. Physical chemistry is all color calculation. So bad maths, you die. 3 times positive 2168, right? Plus positive 994. 994 plus positive, so 2 times positive 218, sorry, plus LE. See now, right? Can find it. So now let's check the answer. I think it's here. Right, see now, okay? So now the whole thing here and the whole thing here, right? You can work it out. It's very big. Okay? Okay? So I've taught you how to define. I taught you how to draw the cycle. I taught you how to write the equation of this energy, and I taught you how to calculate for different kinds. Okay, from NaCl to Na2O to magnesium chloride to magnesium nitrate. All these are different from barium nitrate. All this. Okay, you can do more examples by yourself. Right? I finished this part of this energy. The next time I didn't have time to go through the factors that affect it. I'll do it the next one. Right? Okay. Bye bye, and I'll see you